Transformers are very important to our use of electricity in general, and I'm not referring to Optimus Prime and Bumblebee and all of them. But transformers are important because they change the voltage that you're dealing with. And the reason that's important is because, well, you need to have a certain voltage, for your appliances. Most are set, and our outlets are set like this to be either 120 volts or maybe 220 volts, whereas the power transferred down power lines can be as high as 750,000 volts, and so we need to be able to transfer between these voltages. Now, when we transfer, when we go through a transformer, what's held constant is the power. The energy transferred can't, change through the interchange. You can't get out, if you put in a certain amount of energy, you can't get out more energy than that. And in the transformer, the power is thus held constant. There's only so much energy transferred down. So if we're at a higher voltage, that means we have a lower current. Now, in the power line itself, we go through our transformer, and then we're just going through our power line, which has some resistance, right? And the energy lost as heat in that wire. So this is referring to power on one side of the transformer versus power on the other side of the transformer. Now I'm talking about the power dissipated as heat in the power line. Well, since the resistance is what we know, we can think of that as I squared R. And so we want the current to be as low as possible, which is why we have a super high voltage, because then the current passing through it will be smaller, and so then there's less energy dissipated as heat in our power lines. That's why there's such a high voltage used in power lines. Now, what a transformer looks like, more or less, is that you have an iron or some other conducting, magnetic substance in a ring, and on one side you have wires wrapped around, and they're in their little circuit, and on the other side you have wires wrapped around in their little circuit. My beautiful drawing skills, which I know you all are enamored of. Right. And there's an inductance that happens in these two coils. And so the flux through those coils is basically the same. That's originally what we talked about with Faraday's law and everything. We know that the EMF induced is equal to minus N delta phi over T. Right? That was an equation we worked out a long time ago. So one coil, we call that the primary coil. We have some EMF, the primary voltage, and the number of coils in the primary thingo. And then this flux is just flux. It's the same for both coils, and time is the same time. So in the secondary coil, like I said, so primary, secondary, we have the same flux. And so if we solve this for flux over time, we've got a negative flux over time, I guess we could say. We can say that this is equal to change in flux over time. And we can also say that this is equal to change in flux over time. So this kind of gives us the transformer equation. If we just rearrange this a little bit, the voltage in the primary coil over the voltage in the secondary coil is equal to the number of turns in the primary coil over the number of turns in the secondary coil. So the voltage you get is just proportional to the number of turns. If you have half the number of turns in the secondary coil, you're going to get half the voltage in the secondary coil. If you get double the number of turns, you're going to get double the voltage. Right? So voltage is stepped down or stepped up. Now, we don't get free energy. The power passing through the power going on in those coils is IV. So that means that, and that power is the same, so we can say this: the current in the primary coil times the voltage in the primary coil is equal to the current in the secondary coil times the voltage in the secondary coil. And so we can see that the primary voltage over the secondary voltage is equal to the current in the secondary coil over the current in the primary coil. And this altogether is our transformer equation. And all of these ratios hold true across a transformer. So stepping up the voltage decreases the current, and vice versa. Now, in order for this to work, there's this delta phi here. We kind of ignored it, but if delta phi is 0, if there's no change in flux, then there's no induced EMF. So the flux does have to be changing, which means that the current has to be changing. So that means that DC, direct current, DC cannot be transformed like this. You can't step up or step down the voltage. Only an alternating current can be transformed, which is why we use alternating current in a lot of things. So this alternating current, the fact that this is alternating current is very important. Any problems involving transformers will basically just be a simple application of these ratios. And like I said, transformers are very important because it saves us energy loss when we transfer power at these high voltages, but we need these lower voltages to operate our appliances.